Okay, so a little bit later than anticipated. So apologies for that, but we'll get through this quickly. So I've decided that we'll just keep it relatively simple for this one, that we'll just look at the physics of how you keep a satellite in geostationary orbit. And then when we come back on Monday, we'll talk a bit more about satellite motion in general, because there were some points I didn't quite get to last week about that, and we'll look at other types of satellites, orbits, and then that'll be it for topic 1.3. We can start to think about doing special relativity, and then we can start to think about doing our first summative test. All right. So as we talked about last time, a geostationary orbit is an orbit where the satellite in that orbit will have an orbital period of 24 hours, which is the same as the time it takes for the Earth to spin on its axis once, which is also known as the Earth's period of rotation, which is also known as 1 day. So because the orbital period of the satellite is 24 hours and 1 day on Earth is 24 hours, that means it basically sort of like keeps pace with the Earth as it rotates. And that means from our point of view on the Earth, it appears that the satellite is in a fixed position in the sky above us. It looks like it's hovering above the ground. In reality, it's not fixed, it's moving, but it just happens to be moving at the same speed that we're moving, with the same period that we're moving. So the advantage of that is that if you have a satellite dish on the Earth's surface that's trying to make a connection with that satellite to either upload or download data, that satellite just needs to be pointed to a fixed position in the sky where the satellite is, and then you'll always have a constant connection to that satellite. It doesn't need to rotate or move, because from our point of view, the satellite doesn't move in the sky. And we can see that in this animated image on the side. So this would be a geostationary satellite that's in orbit, geostationary orbit, above North and South America. So from a point of view of someone in North or South America, that satellite would be in a fixed position in the sky, and it's just hovering there and never moving. All right, so that's the basic idea. But what do we actually use geostationary satellites for? And then we'll look at what are the requirements to have a satellite in geostationary orbit and remain in that orbit. So basically, we use geostationary orbits for any applications where we want a constant position of the satellite above the Earth. So we want to just be looking at one particular area on the Earth always. So that could be TV or radio signals. So that's not such a big deal anymore, but in the old days, because these days we get a lot of our TV and radio through Wi-Fi, right? Like if you want to listen to music, you do it on Spotify. If you want to watch, shows or movies, you do it on Netflix. So this is all coming through the internet for most people. So either coming through like fixed cable internet, like the NBN, or it's coming through mobile internet, like 5G. But that's how we do it mostly. So this is becoming a little bit outdated, but you can still get satellite TV like Foxtel, and you can still get satellite radio. It's not such a big thing in Australia, but Sirius XM is a satellite radio station that used to be really popular in America, and I think it's still going. So you would have satellites in geostationary orbit that are beaming down TV and radio signals to the country below. Now, you can also use geostationary satellites for communication in remote areas. So if you're out in the outback, you're not going to have any NBN lines going out there. You're not going to have any mobile phone towers out there. So you won't be able to make calls on your phone. So if you're out there, doing adventure, forward driving or something like that, you need to take a satellite phone with you in the case of an emergency. So if something goes wrong, you can make a call to get help. There won't be any mobile phone reception, so you send a signal up to a satellite in geostationary orbit above Australia, and then it relays that signal onto the police or emergency services or something like that. If you live full-time in the outback, where there's no mobile phone towers or anything like that, you're going to rely on the satellite for all of your communication all the time, including internet signals as well. So, what's it called? So Telstra, the big telecommunications company in Australia, launched a geostationary orbit satellite called SkyMuster, I think about a decade ago. And that provides telephone and internet to people that live in the middle of Northern Territory and places like that, because that's the only way they're going to get signals. So that's in a geostationary orbit above Australia. And then the last one is for surveillance, so looking at things below us on Earth. Now, as we'll see in a second, geostationary orbits have to be really, really, really high above the Earth to achieve that orbital period of 24 hours. So at that height, you're not going to be able to like spot individual cars, if you're a spy satellite or something like that, or individual tanks if it's a military satellite. I think the average pixel size, like, how big a single dot on a satellite image is for something in geostationary orbit is like 10 to 100 meters. So each pixel is like 10 meters wide in real life, up to 100 meters wide in real life. So it can't be used for a lot of things we use surveillance satellites for, but it is particularly good for meteorology, which is basically the science of weather forecasting. So the Bureau of Meteorology, or the BOM, the Australian government organisation that does weather prediction and weather monitoring, uses signals from a Japanese geostationary satellite called Himawari 9. Because if you think about it, we are in about the same position on the Earth as Japan is. Japan is above us, but in terms of east-west, we're in about the same position as Japan. So we can get some time on the Japan's geostationary satellite, and we can get images of what's happening below on Australia. So we can look at, that hasn't turned out quite as well as I hoped, but if you had a full res picture of that, you can see cloud patterns and rain and stuff like that on Australia. So BOM uses images from this geostationary Himawari satellite to look at what's happening in Australia weather-wise, and then use that to make predictions about what the weather's going to be like tomorrow or the day after and so on. So these are our main kind of applications. So requirements for a geostationary orbit. So the first one we know is that it has to have an orbital period of 24 hours. We'll get to how you achieve that in a second. But it also needs to rotate in the same direction as the Earth does as well, right? If it has an orbital period of 24 hours and it's rotating in a completely different direction to the Earth, it'll take 24 hours to go around the Earth, but it won't be in a fixed position above us, right? It has to rotate with the Earth. So the Earth, if viewed from above, like if you looked at the Earth from above the North Pole, look down on it like that, the Earth rotates anti-clockwise. Because think about where the sun comes up in Australia. The sun comes up in Australia first in the eastern states, Victoria and New South Wales, then in South Australia, and then Western Australia is last. So like morning in Victoria is earlier, or sunrise in Victoria is earlier than sunrise in Adelaide, which is earlier than sunrise in Perth, right? Now, we know that the sun isn't actually moving from east to west. And what's actually happening is the Earth is rotating in the opposite direction, and it makes it look like the sun is moving. So if the sun appears to go from east to west across the sky every day, then what's happening is the Earth's actually rotating in the opposite direction. The Earth's rotating from west to east. So when viewed from above, that turns out to be anti-clockwise. So the Earth rotates anti-clockwise, which means the satellite needs to revolve or spin around the Earth in an anti-clockwise direction as well. And we can see that on this diagram here. And then the last thing we need is that the plane of the satellite's orbit needs to align with the Earth's equator. So in this animated diagram here, we've got two kinds of satellite orbits with a period of 24 hours, geosynchronous and geostationary. So geosynchronous has an orbital period of 24 hours, but it doesn't line up with the Earth's equator, so it doesn't appear to be in a fixed position. Whereas the blue one there is a geostationary orbit. So if you're inclined at 0 degrees to the equator, and you're orbiting anti-clockwise, because the Earth rotates anti-clockwise, you will have achieved a geostationary orbit, and you'll be in a fixed position above the Earth's surface. All right, so there are 3 requirements. So 1 and 2 are pretty obvious. For 3, how do we work out how high above the Earth our satellite needs to be to have an orbital period of 24 hours? Well, we use Kepler's third law, right? Because Kepler's third law, you remember from last week, relates the orbital period t to the orbital radius r. And we can see that as the orbital radius gets bigger, the period gets bigger as well. So some of the satellite examples we've looked at so far, we've had satellites that have been like 300, 500, 1,000 kilometers above the Earth. And they've had orbital periods in like the 1, 2, 3 hours. So if we want an orbital period of 24 hours, it's going to have to be a lot higher. So what we do is we take Kepler's third law, we rearrange it to make r cubed the subject, and then take the cube root of that. So we get this where my cursor is. That's going to be the equation we're going to use. And we're going to solve for the orbital radius for a geostationary satellite with an orbital period, capital T, of 24 hours. But 24 hours has to be converted into seconds because time is always in seconds in physics. So we go 24 hours in a day multiplied by 60 minutes in an hour multiplied by 60 seconds in a minute equals 86,400 seconds. That's that orbital period T, and then we insert that value into our orbital radius equation here. We crunch the numbers, remembering that it's a cube root rather than a square root. I actually made that mistake myself earlier today when I just double checked the working out. And then when I do that, I get, as my final answer for R, 4.22 times 10 to the power of 7 meters, or 4.22 times 10 to the power of 4 kilometers, which is 42,200 kilometers. So that's telling us that the orbital radius is about 42,000 kilometers for a geostationary satellite. Okay, now, usually when we talk about a satellite, we don't talk about its orbital radius because that's measured from the center of the Earth. We actually talk about its orbital altitude, or its height above the Earth's surface. So we got one last little step here, which is to subtract off the mean or average radius of the Earth, that's RE, which if you look on your physics formula sheet is 6.37 times 10 to the power of 6 meters, or 6,370 kilometers. So to find the orbital radius h, I've gone R, take RE. Note that this is in kilometers rather than meters. I can't remember why I did that, but anyway, just be aware of that. So we go 42,240, take 6,370, and that gives us an approximate value for our orbital altitude of 35,870 kilometers above the Earth's surface, which is significantly higher than most low Earth orbit satellites, which have an orbital altitude of about 1,000 kilometers or lower. So this diagram here kind of summarizes that. So in this diagram here shows different kinds of orbits. A lot of our satellites will be in low Earth orbit, which is this little bit here, just outside the Earth's atmosphere, used mainly because it doesn't require a lot of rocket fuel to achieve these orbits compared to other kinds of orbits, which means it's not too expensive to launch them, because the further you have to launch a satellite, the bigger the rocket and the more rocket fuel you need, and therefore the more expensive it becomes. And launching any kind of satellite to orbit is very, very, very expensive. We are talking thousands to tens of thousands of dollars for every kilogram. So that's low Earth orbit. Then we've got a medium Earth orbit. And all the way out here, we have our geostationary or geosynchronous orbits here, right? So you can see that this is where our geostationary orbit is here, where my cursor is. Low Earth orbits are over here, so it's much, much, much further out. And then beyond that, we have what we call high Earth orbits, which are extremely rare. There was one of these super secret CIA military space planes that the US government was testing last year, and that was in some sort of weird high Earth orbit that went like way, way, way out beyond the geostationary thing. But no one knows what they were using that for, whether it was just a test or they're actually using it for some sort of military application. But it's very rarely used by commercial satellites. And then if we look down the bottom, all of this bit here is basically squeezed into that part there. And then from over there, for reference's sake, we can see how far away the moon is. So this kind of explains why we're not going to the moon every week, because it costs a lot to get into low Earth orbit, and low Earth orbit is a tiny fraction of the way to the moon. So going to the moon is extremely expensive. All right, moving on. So we can then use either Kepler's second law, or in this case, we've just used the simple circular motion equation, speed equals distance, or the circumference divided by the time, the period. And I've put 86,400 or 1 day down there for the period, and that gives me a velocity for a satellite in geostationary orbit of about 3,000 meters per second. So a satellite in geostationary orbit needs to be moving about 3 kilometers every second to stay in that orbit. So that's our calculation part done. These are common sorts of questions that we might ask you in a test or an exam situation. Derive or determine the orbital altitude or orbital velocity for a geostationary satellite. Now, before we finish up, let's just talk about disadvantages of geostationary orbits. So why is it so rarely used compared to other sorts of orbits? Well, firstly, extremely expensive to launch a satellite to such a high orbit because it's so far away from the Earth and it requires lots of rocket fuel, and in particular it needs to use a staged rocket as well. So for low Earth orbit, you can have one big old rocket that basically takes off from the Earth, burns off all of its fuel, and then the satellite itself has a little kicker rocket that launches away from the main rocket and gets it into orbit. But it's not super complicated. Whereas if you want to go to geostationary orbit, you're going to have a rocket on top of your rocket, and then that second rocket launches once you get outside the Earth's atmosphere, and then that takes it to geostationary. So it's a lot more effort, a lot more cost, a lot more fuel. Also, as well, extreme distance from the Earth makes it unsuitable for many surveillance applications. So as I said earlier, because it's so far away, even with the best cameras we have currently, each pixel on your image is about 10 meters. So you can't use it, as some surveillance satellites can, to like pick out individual cars on a street in like Iran or something like that. It doesn't do that. So it's okay for meteorology, but not okay for military and spy surveillance stuff. We've also got the fact that the time delay, even at the speed of light, between sending data up to the satellite and getting it back on the Earth is about a quarter of a second, which is what we call high latency. Latency is a delay in sending a signal out and receiving a signal back. So it's not suitable for high-speed data transmission. So you're not going to get like NBN type data uploads and download speeds if you're using a geostationary satellite for your internet connection. And you're definitely not going to get that ping you want to pwn noobs and get headshots in Fortnite or something, right? It's not going to work. And then lastly, not ideal for observing or communicating with regions near the poles. Because remember, our geostationary satellite is above the equator. If you're above the equator, you're looking at the poles, the north and the south poles, at a very extreme angle, and it's not going to be, you're not going to have a lot of luck observing the poles, and you're definitely not going to have a lot of luck communicating at the poles either. So let's suppose I want to observe what's happening around the poles. I would put a satellite into a polar orbit instead, which we'll talk about next lesson. Okay, so many satellites do not use geostationary orbits for these reasons, but for certain applications like communication in distant regions, they work extremely well. All right, so what do we need to do now? Well, go onto the Google form that I've put up on Google Classroom, respond to the questions there. There's just a handful of them, and do this before midnight on Sunday because I will be checking it on like early on Monday morning. As when I say early, I mean like 4, 5 o'clock in the morning. And if your response isn't listed there, we will book you into the Learning Center, and there will be no if, buts, or maybes this time around. Okay? So do not forget.